In this video, we will learn about the weak acid and base approximation. We'll start with percent ionization though, as it will be a needed definition to talk about the approximation. This is going to make many of our future calculations far, far simpler. The objectives in this video are first to give you the ability to describe percent ionization and calculate it for simple conceptual problems. After we've introduced this topic, we'll connect it to the weak acid and base approximation. I will hand wave through one problem, giving you the answer, to show you why this is an acceptable approximation to use, and then we'll save the actual calculations for weak acids and bases for the next video. Percent ionization is really just another way of talking about the strength of an acid or a base. If a certain amount of the acid breaks up, we can simply put the amount ionized over the total amount that was initially present. Then, of course, multiply by 100 just to turn it into a percent. We'll do some real examples in a moment, but for now, let's just make sure you have the concept down. Now just remember, of course, that this is actually a dynamic equilibrium, so there's a constant dissociation and reassociation. But this would be like a freeze frame of one particular moment in time. And obviously, there are way more atoms than shown here. However, this will just get the basic concept across so that we can move on with real calculations. We can count how many atoms are ionized, in other words, here 3, and how many were initially present, or 14. We can then do 3 over 14 times 100 to give us the percent, giving us 21.4%. Let's look at this as a formula just for completeness sake as well. Let's write down the formula for percent ionization of nitrous acid in ammonia. We'll put the amount of dissociated acid, or in other words, we can just say the nitrite ion, over the initial amount of HNO2 and multiply by 100%. Because we just want the number of dissociated atoms, we only put the nitrite on top, not the H+. Now let's do the same thing for the ammonia, or the base. Here we put the ionized quantity, the NH4+, over the initial amount of NH3 and multiply by 100%. Be careful to note that this is the initial amount of acid or base, not the equilibrium value like for Ka or Kb. Now let's think about what the percent ionization tells us, and specifically, what happens if it is very, very small. If barely any of the acid dissociates, we get a low percent ionization. So almost all of the species are non-ionized. In this case, I'm going to talk about the acid example, but the exact same idea is true for bases. Because of this, the amount of HA at equilibrium is now the same as that initially. I say about because, of course, it has some dissociated, yet it's nearly identical. Since it is this close, we will often be able to say that they are equal within the limits of acceptability for our problem. Let's quickly talk about how this relates to Ka and Kb. They are both measures of the extent of dissociation, and because both contain products in their numerator, as the reaction is shifted further to the right or further to the products, both values increase. Or in other words, a low Ka means a low percent dissociation, and a high Ka means a high percent dissociation. In mini summary of the past few slides, if very little of the acid or base is ionized, percent ionization and Ka are both small. And this means that the change in Ha is very small. So the amount of the undissociated acid at both initial and equilibrium conditions is very small. Now, I do want to take a moment to point out a concept that can be confusing. Even though we are saying that the amount of HA stays the same, we can't say that about H+ and A-. Why? If all the H+ and A- is coming from HA, and therefore is technically changing by the same amount, why does HA stay the same, and yet H+ and A- don't? For this, I'd like to use an example of money. If Bill Gates gives you $1 million, he still has the same amount of money he started with. Sure, it was $1 million, but that doesn't have an appreciable effect on his wealth. You, on the other hand, have just received a very large quantity of money in your world. So although the same amount of money was taken from one person and given to another, the amount, when compared to the original quantities involved, are a different percentage. Now that I've told you all of this, you may be wondering, why do I care? Where is the part that she promises that this will make my life easier? Let's do a quick example where I show you the answers without going through all the steps to get there, to drive the idea that this is helpful home. And in the next video, we'll use this to do some more detailed and complex calculations, making them much simpler via this approximation. Let's say that we have a 1.0 molar acid solution with a Ka of 1.8 times 10 to the negative fifth. At equilibrium, it has the concentration of A minus of 4.24 times 10 to the negative third. Next video, we'll be calculating this out, but for now, just believe me. This means that the final concentration of the undissociated acid is the initial amount minus the ionized amount, or 0.99576, which when rounded to account for sig figs gives us 1.0. Or the same thing that we started with. It is important to recognize whenever you make an assumption, you must have an awareness of when it is and is not true. We've already discussed the effect of Ka and Kb, that in fact they must be low for the assumption to be true. But there is one more aspect that we must understand. What dependence on concentration is there? Because of the kinetics of the equilibrium system, if the concentration is very low, there is actually a lot of ionization. So a very low concentration of weak acid still has an extremely high percent ionization, and the approximation is not valid. You can see on this graph in the initial low concentration area, in this area here. So how do we know when we can and cannot use this approximation? There are two ways that we can decide if the weak acid approximation is valid. The most commonly used one, and the one that I'm going to require that you show me whenever using the approximation in the calculations that we'll be doing next video, is the 5% ionization rule. Once you find the equilibrium concentration of A minus, the percent ionization must be less than 5%. That ensures that we are in this area of the graph. However, there is another extremely handy guideline that you can use as a quick check before beginning the process. We said that a low Ka and high concentrations are both required for the approximation to be true, and it turns out that these need to differ by a factor of about 1,000. Or in other words, you can put the concentration over the Ka and see if it's 1,000 times greater or larger. You can do this via estimation simply by looking at the order of magnitudes to decide if it is worth using the approximation or not before even starting the problem. You then must still show me the 5% check after using the approximation. You should now be able to describe the concepts behind percent ionization and calculate it for problems where the information about the initial and final concentrations are given, and connect this to the weak base and acid approximation. In the next video, we'll start doing more complex problems using weak acids and bases and the approximation we discussed here to make our calculations simpler.